Hey there, welcome back to Short Text 331. Today we're going to be talking a little bit about the Dirac delta. This is going to be a short video, and I just want to cover a little bit of this material that you'll find everywhere on the web, actually. But we've talked about the Dirac delta off and on here in previous videos, so I figured let's do this at least for completeness. So here we go. Remember, we talked about the Kronecker delta a while back, and if you don't remember that, that's okay. If you didn't see a video talking about the Kronecker delta, that's fine. It's really a very simple object. The Kronecker delta is simply this type of thing called delta ij, and it's an object that takes the value of 1 if I is equal to j and 0 otherwise. And this is really used a lot of the time to just denote the identity matrix. These are the elements of the identity matrix. If you think about it, the identity matrix has 1 on the diagonals and 0 everywhere else. And so that's it. This is what that is. Is that delta ij is then basically the identity matrix. And the Dirac delta is similar in a way. The Dirac delta is an object that is a function of a continuous variable now, and it's such that it's defined to be delta of x equal to 0 if x is non-zero. Delta of x is 0 if x is non-zero. So it's basically 0 everywhere except at 0, and at 0 is not defined. It's actually given by this type of equation. The integral from minus infinity to infinity of the delta of x times f of x dx is equal to f of 0 for a sufficiently well-behaved function f of x. And let's say that f of x is just a continuous function. I'm just going to leave it at that. That's a continuous function for the purposes of this series of videos. It doesn't have to be differentiable. It doesn't have to have any special properties in reality. It doesn't even have to be continuous in reality, but let's assume it's continuous just for the sake of this video and this series of videos. And in particular, what you have is the integral from minus infinity to infinity of delta of x dx is 1. Now we know that away from the origin, away from x equal to 0, delta of x is 0. So you really have this property in reality. That is that the integral from a to b of f of x delta of x dx is f of 0 if the 0 is contained in the interval a, b, and it's 0 otherwise. And it's the same for this type of identity. The integral from a to b delta of x is going to be 1 if the interval AB contains the origin, and it's 0 otherwise. And so that's basically it. And of course, I'm assuming that A is less than B, otherwise instead of getting 1, you would get minus 1, because you flip the order of integration as you flip the interval as usual. That's no different. And this delta can be shifted, of course. We can shift the delta to saturate as at x0 instead of at the origin. That's what we say, by the way. That's the language that we use. We say that the delta, this type of delta of x, saturates at 0. So at 0 is where it has all its weight. And away from 0 is 0 everywhere. So it doesn't really matter so much out there. But here, delta of x minus x0 saturates at x equal to x0. And so this integral from a to b of f of x delta of x minus x0 is simply f of x0. If x0, of course, is contained in the interval a, b, and it's 0 otherwise. So how do we understand this weird object? At first, it might seem like a very weird thing, because it vanishes everywhere except at one point, and that point is singular enough to guarantee that you have all the weight there, and the integral of that object is 1, and the integral of that object multiplied by a function. It's just a function evaluated that at the origin, at that point where the delta saturates. So how do we understand that? And one of the easiest way to think about this is really as a limit. So let's define a sequence of functions, dn of x, where we have x as a variable and n is our series index. And so we're going to make that function be equal to n if x is in the interval minus 1 over 2n, 1 over 2n, and it's 0 otherwise. So basically, if you were to plot the n for a fixed n, it was going to look like this. This is what a plot is roughly going to look like. It's going to be 0 here, 0 on the other side, and it's going to look like this square, or rectangle really, here in the middle. So the rectangle has size 1 over n, as you see here, and height n. And so that's why when you do the integral from minus infinity to infinity of dn of x dx, you see that the result is simply the area under this curve. And the area is just the area of the rectangle, which is the height by this width. And so that's n times 1 over n, which is 1. And it's 1 for all n. And so now we can comfortably take the limit n going to infinity And what you see is that when n goes to infinity, this interval where the function is non-zero becomes smaller and smaller and smaller. And in the end, in the limit that n goes to infinity, the function dn of x becomes a function that is zero everywhere except at x equal to zero, where it basically went to infinity. And it's always such that for all n, so every step of the way as you take the limit to infinity, the integral is 1. And so you still have that property in the limit. And so that's one way to think about the delta, the Dirac delta, as a limit of a sequence of functions. Other representations with the same philosophy, the same idea, could be given in terms of Gaussians or Lorentzians, which roughly both have the same shape, roughly speaking. So they have a hump here in the middle and they go to 0 again. Of course, they do so at different rates. Gaussians and Lorentzians are different, but roughly speaking, the picture that you would see is something like this. And for the case of Gaussians, they would look like this. There would be a prefactor here, a normalization factor, and a decay type factor C sub n, and then it goes quadratically with x. And so when x goes to infinity, this decays, and minus infinity as well. And if you make Cn go to infinity, as n goes to infinity, then the decay is going to be very abrupt. And so that decay goes to 0 very, very quickly when Cn is made very large. But you can tune an, which is basically the value at 0. If you think about it, if you put x equal to 0 here, you recover an. So this value here is just an. Now if you tune an as a function of n so that this integral is 1 for all n, then you're back in the same type of situation that we had with our rectangle. In other words, we can guarantee for the Gaussians that their integral is going to be equal to 1 for each value of n as we take the limit and make Cn large. In other words, this an is going to depend on what this Cn is, and then you can make Cn whatever you want and take n to infinity and make Cn very large, and then an is also going to be very large, but the area under the curve is also always going to be 1. And what's going to happen as you take that limit is that this hump gets taller and taller and taller, and it grows narrow as you make n very large, and so that converges then to a representation of the Dirac delta. And if you are wondering how do you use that representation, well, you basically use these Gaussians to do all the calculations that you need to do, and then you take the limit at the end. And the same with the Lorentzians. Lorentzians are curves that look like this. So roughly they have the same type of schematic behavior, and at x equal to 0, the value is 1 over bn, as you can see here. But when x goes to infinity, then they go to 0 on both sides. And so all you need to do is to make sure that bn goes to 0 when n goes to infinity. And you can do that at any rate you want with n. Just make sure that bn goes to 0 as n goes to infinity. And we can take, for example, bn to be n, or n squared, or whatever you want. And as written here with this 1 over pi, this is already normalized. That is, it's already true that the integral from minus infinity to infinity of ln of x dx is equal to 1. Okay, so it's already true. And so that normalization is done, and we can make with bn whatever we want as long as it goes to 0. So let's say that bn is goes like 1 over n or 1 over n squared. And so that's, at that point, that's ready to go. As n goes to infinity, that goes to 0. And so we can then proceed, and we have a representation of the Dirac delta. So here's a quick application of this. Recall that with matrices, if you have a linear system of equations, then it would look like this. You have AV equals W, where W is your right-hand side, A is your matrix, and V is your unknown. Usually I call this X and I call this B in previous videos, but here to make sure you stay on your toes, I changed the notation a little bit, but I'm still calling the operator A here. So let's say then you have AV equals W, you have to find V, and so finding V amounts to putting A on the other side of the equation, and so that is V is equal to A inverse W, and where A inverse, of course, is such that A inverse is equal to A inverse A, which is equal to the identity matrix. And in terms of indices, explicitly what this looks like is like this. So the element I, or the ith element of V, is the sum over k of A inverse ik times Wk. Wk is given to us because it's part of the right-hand side of the equation. We're tasked with finding V, and so once we arrive and once we have A inverse, then we can do this calculation, and that gives us V sub I. Now, this is not the application. This is just a reminder. The application is what happens when you have a differential operator instead of a matrix here. So suppose you have our differential operator d hat here, and for example, this could be the Laplacian. or some other derivative, or a more complicated Laplacian plus something else type operator, and phi is our unknown, phi of x, and rho of x is given to us. And this could be the case where you have, for example, a charge distribution, rho of x, and we have to find phi. Okay, so then we need to put d on the other side of the equation. So what's d inverse? Well, we saw in a previous video a first bit of what the inverse is. So applying the inverse to f, in other words, applying the inverse to rho in our problem, amounts to doing this integral from minus infinity to infinity, or in whatever interval you're working on, of a function that's called a Green's function, g of x x prime, which completely characterizes the inverse, multiplied by f of x prime dx prime. And the characteristic property of this function, g of x x prime, is that when you apply the operator, the hat, our differential operator, you get delta of x minus x prime. And you see that has to be the case, because if you have this property, then you can apply d to this d inverse f, and then that d goes straight to hit x here. Remember that if you have this integral, which is the inverse applied to f, so this whole integral is that, it's the inverse applied to f, but it depends on x. It doesn't depend on x prime. X prime has a bit integrated, but depends on x. And so this operator d acts on x. And when it acts on x, on this g of x minus x prime, or g of x x prime, we obtain delta of x minus x prime. And by the property of the delta, and this is the application, we get that the integral from minus infinity to infinity, delta of x minus x prime, f of x prime is just f of x, which is exactly what it should be, because d inverse f has to be just f. So this is exactly working as it should, provided the d applied to g is the delta. And once you have this property that's guaranteed, then you're ready to solve your problem. And in other words, if you solve this problem for g of x minus x prime, or gx x prime with the delta x minus x prime on the right hand side, then you can solve for any rho whatsoever, because by virtue of this equation, now applied to our case, we have that phi of x, which is the inverse applied to rho, then is equal to the integral from minus infinity to infinity of g of x x prime rho of x prime. In other words, I just rewrote this equation where now f is rho, and we're looking for phi, and so that's the solution to our problem. So the inverse applied to rho, here's the inverse applied to f. I use f here, but imagine that this is rho, and so that's what I wrote down here. The inverse applied to rho is just phi, is what we're looking for, and it's the integral over minus infinity to infinity of g of x comma x prime rho of x prime dx prime. And that's the general solution for our problem. And where I'm assuming that we don't have any boundary conditions to worry about, other than whatever is already happening by virtue of what's encoded in g of x prime. So I made this integral go from minus infinity to infinity. Usually you may have a fixed interval from a to b, for example. It could be a fixed region of space if you're in 3 dimensions, for example, with some boundaries. And then in that case, you have to be careful about whether there need to be more terms to account for the boundary conditions, or whether the boundary conditions are already built into g by virtue of solving this equation with the appropriate boundary conditions. This is typically the problem that you will find in electrodynamics. In the famous book by Jackson, there's a lot of information on how to solve these boundary value problems and calculating Green's functions and so on for electrostatics. It's a classic problem in graduate level physics. And then it gets, of course, richer and more interesting when you go to electrodynamics, but these Green's functions always appear in this area of classical physics, and they make an even more important appearance in quantum field theory. So the more you become familiar with Green's functions, the stronger your toolbox will be. And that's about all I have for today. I hope you enjoyed this video. If you did, please like and subscribe. And if you're looking for a tutor in physics or math in English or in Spanish, then maybe I can help you. You can contact me at shorttext331@gmail.com, or you can leave a message in the comments section below and I will get back to you. Until next time.